So I know this is kind of confusing because I did sampling distribution of proportions first, but now I want to talk about the sampling distributions of means. So when you take a sample, the center of the distribution, the mean, can vary from sample to sample. And if we took all of those means and made a distribution of them, we look at this sample distribution of the mean. Well, the shape of the underlying population actually comes into play when we're talking about means. So this one gets a little bit trickier than the proportions. So that's why I wanted to do proportions first. Suppose a simple random sample of size n is to be taken from a large population in which the variable of interest has a mean of mu and a standard deviation of sigma. Then the sampling distribution of sample x bar will have the following properties. The distribution will be approximately normal. The mean will be the same as the population mean, and the standard deviation will equal the standard deviation divided by the square root of n. Now note, the shape would be exactly normal if all of the samples, sample sizes, for all the sample sizes when the population itself is normal. But if we don't know if the population has a normal distribution, then we can only say it'll be approximately normal. And that's only if we have large sample sizes. The necessary sample size depends on how non-normal the population is. So there's a guideline we use that n needs to be greater than or equal to 30 unless the population is very non-normal, and then we'd have to get even larger than that. So the conditions for normality. The population of the measurements of interest must be normally distributed. If we knew that, then we knew everything was going to be great. But if the population of interest is not normally distributed, the sample size needs to be large enough. Because remember that law of large numbers, the more samples you get, the larger the sample size, the more normal it becomes. 30 is usually used as our knowledge. Don't ask me where they came up with that. But if you have more than 30, that's great. As with the central limit theorem for a population proportion, the central limit theorem for sample mean species, that should be specifies, oh my goodness, specifies three things: the shape, the center, and the spread. The first step in any CLT problem is to identify which version of the result to use. Determining this involves asking whether the question is about a sample proportion or a sample mean. Oftentimes you'll see the word proportion or mean, but not always, so we have to be very careful of that. Then we have to verify our conditions. The population must be normally distributed, or if we don't know that, we need a sample size of at least 30. Now, do not confuse the two versions of CLT. The key difference between them is the type of variable involved. So, CLT for sample proportions applies when the underlying variable is categorical, usually. And sample mean usually applies when we're talking about quantitative data. So those are key things to remember. Now, let's get into the root of it. So, when we're sampling for a long time, that law of large numbers comes into play. The sampling distribution for sample means tells us how much variability in possible samples means to expect for different sample sizes. There is a much simpler technical result called the law of large numbers, which guarantees that the sample mean, that should be x bar, will eventually get close to the population mean. So, if we can get close enough, a large enough sample, and remember 30 is our guideline, we're going to get really close to having this work out perfect. The law of large numbers says that for any specific population, the larger the sample size, the more you can count on the sample mean being an accurate representation of the sample of the population mean. Okay. A randomly selected sample of 60 individuals over 65 years old take a test of memorization skills. The sample mean is 53, and the population standard deviation is 7.2. Give the numerical value of the standard deviation of the mean. So our first question, is the sample large enough? Is n greater than 30? And the answer to that is yes, it's 60, which means that the shape is going to be normal. It's going to be a bell curve. The mean equals the mean. In other words, my x bar is going to approximately equal the population mean. And we can find the standard deviation if we know the population standard deviation divided by the square root of n. So, since we are greater than 30, we can use this formula to find the standard deviation of the mean. So, we would take that 7.2 divided by the square root of 60. And I know I left my calculator out here somewhere. Here we go. 7.2 divided by the square root of 60, and we get 0.9295, and I'll just go with that. Small planes cannot fly well if the payload, which means how much people, luggage, and fuel have, that weighs too much. Suppose that an airline runs a commuter flight that holds 40 people. The airline knows the weights of passengers plus luggage for typical customers on this flight is approximately normal. So since we know that the population is approximately normal, that's awesome, with a mean of 210 and a standard deviation of 25. This is population information. They're saying that from years and years, they know this to be true. The population info says it's approximately normal, and the population mean is 210, and the population standard deviation is 25. Now, can we describe the sampling distribution? In other words, if we took the mean from several samples, what would happen with all of those means? Well, the shape would be normal. The center, in other words, x bar, would be our mean for the population, because we know that the population is normal. And our spread, our standard deviation, could be found by taking the standard deviation of the population divided by the square root of the sample. So we would do 25 divided by the square root of 40, and 25 divided by the square root of 40, and we get 3.95. Assume that customers on any particular, oh, that should say flight, I don't know what happened with the L's, are similar to the random sample. If the total weight of passengers and their luggage should not exceed 8,800 pounds, what is the probability that a sold-out flight, 40 passengers and their luggage, will exceed the weight limit? Okay, so the limit is 8,800 pounds for 40 passengers. What does that mean the average weight is per passenger? The average weight per passenger would be to take that weight divided by the number of passengers, and that becomes 220 pounds. So we want to know the probability of us having a mean greater than 220 pounds. So let's think about what this is. If it's normally distributed, the mean is 210, then 220 would be pretty far out here, right? Because if the standard deviation is 3.95, this would be around 214, 218. We're talking about right here. Greater than 220 would be the probability in this area. And remember, our standard deviation is 3.95. So, we're going to go to the distribution. And since we want a CDF, our lower limit is going to be 220. Our upper limit is going to be 1 times 10 to the 99th, or you can do 1e99. Our mean was 210, and our standard deviation is 3.95. And the probability of having a flight like that is 0.0057. So it's less than 1% would exceed that weight limit. Okay, let's go to another example. Suppose the body temperatures in a population of healthy adults follows a normal distribution. Since they've told us that it already follows a normal distribution, we don't really need to worry about having a large sample size, but it'd be good to have it anyway. But they tell us that the population follows a normal distribution with a mean of 98.6. So that means the population mean is 98.6, and the standard deviation is 0.7. Are those numbers parameters or statistics? Well, since they're coming from the population, those are parameters. And I already showed the symbols to denote them. Calculate the probability that a randomly selected healthy adult from this population has a temperature between 98.5 and 98.7. So between 98.5 and 98.7. I would do 98.5, 98.7, 98.6, and 0.7. And we get approximately 0.114. Now, consider taking a simple random sample of 130 healthy adults from this population and determine the probability that the sample mean falls between 98.5 and 98.7. Do you believe this probability would be larger, smaller, or the same? I want you to think about that. Are the conditions necessary for the validity of the CLT met here? Yes. In two ways. The population is normal, and our sample size of 130 is definitely greater than 30. So awesome. Now, use the sampling distribution to calculate the probability of obtaining a sample mean of 130 adults. So the mean we're going to still use is 98.6, but we need to use a different standard deviation. The standard deviation of the sampling distribution would be to take the population standard deviation divided by the square root of n. So 0.7 divided by the square root of 130. So 0.7 divided by the square root of 130 is 0.06. So we have this smaller standard deviation. Let's see what that does to that probability. Okay, so again, between 98.5 and 98.7, the mean's going to stay the same, but the standard deviation is smaller. And I apologize for those beeps. My computer's giving me some things. This is 0.904. So it's larger. Suppose that we did not know the population followed a normal distribution. Could we still use these values? Yes. And the answer is yes, because the sample was larger than 30. So we are okay. We can still use these values.